I realized that where am I? For the web work that was due today, I somewhat threw you to the wolves a little bit. I realized that. That was a little bit by design. So I know that that's frustrating, but what I wanted you to do is really take a hard look at these and do your best. And then we're just going to do all examples. We're not going to do any new stuff. We're just going to do all examples today and then now you'll get to see me in my reasoning and how I apply things from the toolbox. So what I'm going to do on that web work, I'm going to add 5 points to everybody. So if you got them all, you get 5 extra credit, okay? So it was out of 9. Whatever you got out of 9, I'm just going to add 5 to that, okay? So I understand. So now don't be mad at me anymore, okay? So we got 2 more tools in the toolbox. And the first one is the alternating series test. Let's just review that real quick. Alternating series test says an alternating series looks like this, where this is an alternating series. The alternating series test says that Bn series, which is a positive, that's an all positive sequence, that Bn sequence, all it has to do is decrease to 0. So before we said that wasn't enough. That was necessary but not sufficient. But if it's alternating, then all you need is for Bn to decrease to 0. And then the alternating, so as long as it decreases to 0, the alternating effect then takes care of it and it will converge. So converges for, so this is kind of the casual version, converges if Bn decreases to 0. And if you look at what we wrote it out formally last time, the first condition was that the next term is always less than the previous term. That's the decreasing part. Then the second condition was the limit is 0. So we can just put those two together and say that sequence Bn, it must decrease to 0. And then if it alternates, that converges, okay? So notice, so before the whole thing with the divergence test was if the sequence must have a limit of 0, and then maybe the series will converge, right? That was the whole theme. The only series that converge are the ones whose sequence have a limit of 0, but then that's not enough. Now, with an alternating series, that's enough. All it's got to do is decrease to 0, and the alternating effect will assure that it converges. Does it make sense? Okay, then the next one we had was the ratio test. Okay, and the ratio test is where we looked at the limit of this ratio. And we're going to talk about what this is about. Okay? And then you had this, so you worked on this limit of this sequence, right? So it's like you create a new sequence out of the series, and you investigate the limit of this sequence. If that limit is less than 1, then your series is absolutely convergent. Absolutely convergent. If it equals 1, then the test gives no conclusion, and then if it's greater than 1, it diverges. So let's talk about why that works. Let's talk about why that works. But this is our whole toolbox now. And hopefully what you found was on some of these problems, you're applying more than one. So like you try it with one, it's inconclusive, you got to work on it another. Or you're actually combining 2 of these principles to actually make your final answer, okay? All right, but let's just briefly talk about the ratio test and what's going on with this instead of just having it be this method that we use. Let's just understand it a little bit. So okay, so this thing. So let's talk about this ratio test is very closely related to geometric series. And so let's write the geometric series. Our geometric series looks like this. And we can all write out, so when we see that notation, we all think what? Write it out, practice. So you see that, what that big expression there? What do you think when you see that? Write it out. Write it out. What's your mental image of what's going on there? Yeah, I am. Thanks. Okay, your mental image should be, we're first going to plug in 1, and we're going to get the term. Tell me. A. Then we're going to plug in 2. AR. And what is a series? Add them all up. Then we're going to plug in 3. AR squared. And this just goes on and on and on. Never ends, right? Never ends. And we said that this geometric series converges for what? Converges when? Right. Converges when, we should all have been thinking that. We spent 2 days on that. And so now let's look at the terms. As we proceed in the terms, how does R relate to getting the next term? Look at that. How does R relate to getting the next term in the series? So if you look at any given term, and then you look at the next term, how do those two terms relate? I got AR squared, for instance, and then AR cubed. So how do I get the next term from the previous term in a geometric series? You multiply by R, right? So you come along here, for any given term, if you multiply by R, you get the next term. You see that? And so if that R is less than 1, if you keep multiplying by a number less than 1, you're actually adding what? A fraction of what you added before. Okay? Let's have a test question on what I'm talking about right now. Okay, let's have a test question on this. All right, so then what about if we just have any sequence? We'll start it at 0. How about this? Any series based on some sequence an, okay? So let's write out the terms of that. A naught. Now this is a different A, right? So this A is just our coefficient. This is just our generic notation for any sequence. A1, A2, okay? And then we're going to come down here, and eventually we're going to get to what, say, any term, and call it A sub n, right? And then what's the next term? N plus 1. And on and on and on, right? Okay, so take any pair of adjacent terms, okay? Like this represents any pair of adjacent terms, an and an plus 1. What do you have to multiply an by to get an plus 1? What would you have to multiply an by to get an plus 1? This could be any sequence. It doesn't have to be geometric. Any sequence. So can you form an expression that would represent what you would multiply an by to get an plus 1? So is this an squared? An plus 1 is an squared. No, you don't know that. We don't know anything about this. We don't know anything about this. Nope. We don't know anything about what these terms are like. But if we had to write what's the best we can do to write an expression of what we would multiply that by to get that? So it's just like saying, what do you multiply A by? Not A, so let's say P. What do you multiply P by? P times what equals Q? You have no idea what P and Q are, but how could you express what you multiply P by to get Q? So call it X and solve for X. What does X equal? Q over P, right? So what do we multiply an by to get an plus 1? An plus 1 over an. So our multiplier, just like our multiplier in a geometric series is r to get to the next term, the multiplier in just any series would be the next term divided by the previous term. That would be, you'd form a ratio, and that's the factor that an is multiplied by to get an plus 1. So what we see in a convergence series, if that r is less than 1, it converges, right? If that r is less than 1, if we keep multiplying by a number less than 1, we found it converges. So then what about this? Now this could change, right? In any sequence, that value could change. So we just simply say, as long as the limit of that number is less than 1, as long as eventually it gets to being less than 1, the limit it levels out at a number less than 1, then in the end it's like multiplying by a constant value that's less than 1, right? As long as when n gets big enough, it will converge, that multiplier will converge to a number less than 1. And so then essentially now we are multiplying by the same number less than 1 over and over again for a big enough n. And so it's this basically the same thing. And so then if we do absolute value, then that's basically saying that thing has to be between 0 and 1. Between 0 and 1. So it's just like, so the ratio test is very similar to a convergent, using the idea of a convergent geometric series to do it, right? So if that limit, that multiplier, levels out as something less than 1, then we've got the same situation kind of as a geometric series. Anybody? Does it make sense? So that is essentially the same rule for a geometric series, that your multiplier is less than 1. Does it make sense? So that's what's going on. Anybody have a question? All right, so let's look at some examples from the web work. So we're thinking about our toolbox. Well, this one's telling us, so this one isn't a matter of figuring out what to use, because they're telling us to use the ratio test. Okay, so here we go. So the ratio test, we're going to set up our ratio, and we're going to take the limit as n goes to infinity of an plus 1, which would be 5n plus 1 quantity squared plus 4 times 5 to the n plus 5, and one more 5 there multiplied, over 8 to the n plus 1. And then we'll do, instead of doing the big fraction, we'll do the times version of it, where we times by the reciprocal, 8 to the n over. So when you have these sequences that are big fractions, it's a lot more convenient just to start with, instead of writing a giant fraction of fractions, just start with an plus 1 times 1 over an, the reciprocal of an, which is equivalent to an plus 1 divided by an. Okay, then so we're going to combine the things that are alike. So we're going to get things together that are alike. So what's alike here? So for instance, this right here and this right here. So the 5n plus 1 squared plus 4 over 5n squared plus 4. And then 5, all right, so let's think. 5 to the n plus 5 over 5 to the n plus 4. So they're both of those, 5 to the n plus 5 and 5 to the n plus 4, are just a string of 5s multiplied together. So we just compare how many in the top versus how many in the bottom. So a bunch of 5s multiplied together. How do the number of 5s compare in the 5n plus 5 and the 5n plus 4? You should be thinking there's one more 5 in the numerator, right? If you have n plus 5 5s, that will be one more than n plus 4 5s in the denominator. So then you just have 1, 5 in the top. All right, and so then the rule of exponents is if you have a fraction with the same base, subtract exponents, right? N plus 5 minus n plus 4 is just 1, leaving us 5 to the 1. Okay, same thing with 8. N eighths, you have n eighths multiplied together on the top, and then you have n plus 1 eighths multiplied in the bottom. Results in 1 8 in the bottom. You have one more 8 in the bottom than you do the top. And then we're going to take the limit of that. I was going for room, so we want the limit as n goes to infinity of that. So when we look at this right here, what's our leading term? Our leading term is 5n squared. And so is our leading term 5n squared here. So what's the limit as n goes to infinity? 5n squared over 5n squared. 1. As n goes to infinity, 5 eighths is just 5 eighths. So what is our limit for this one? 5 eighths. So we apply the test. So it's kind of like a geometric series. Eventually r becomes 5 eighths. So it's like a geometric series. Eventually the multiplier to get to the next term, that r value is 5 eighths, which is less than 1. Conclusion? Absolutely convergent. So the limit is 5 eighths. And the ratio test says this thing converges absolutely. Questions on this problem? Questions? So if you're tuned in, if you worked at it hard for today for web work and you're tuned in today, this is going to be a great day because you're gonna fill in all the gaps and you're gonna really start to understand how this works. Okay, next one. But you got to be tuned in, right? Active listening. Next one. Another ratio test. Another ratio test problem. And so we could just okay, we'll come back to it. All right, so we're going to do the ratio test. Here we go. Ratio test. Set it up. And so we've got our -1 to the n plus 1, n plus 1 over n plus 1 squared minus 2 n plus 1 minus 5 times 1, the reciprocal of an, right? 1 over an. It's like dividing by an. Okay, again, combine like things. So since the ratio test is taking the limit of an absolute value, whenever you have these alternating terms, you have a negative, they just go away, right? So that because the absolute value of the opposite of a number is the same as the absolute value of the number. So these, when you've got these alternating factors here, they just switch from negative to positive, negative to positive. They just go away because when our limit is going to be of the absolute value of it. So they just go away, okay? So now all we've got left here is just polynomials. So we're going to look at the leading term in the top and the leading term in the bottom. So the leading term in the top will be, our numerator will go to n cubed, right? Because the biggest term I'm going to get is the n times the n squared. I'm going to get n cubed. And for the denominator, I've got an n squared here, and then this whole thing is also going to be times n. So what's my biggest term in the denominator? Also n cubed. All right, so we basically get the limit as n goes to infinity of We could also, okay, so we could also just group the like things together like I did before, and it's going to be the same result. So let me write it out that way, if you prefer that. So these are hopefully easy limits. Hopefully these are easy limits. N plus 1 over n goes to 1. Leading term, n squared. Leading term, n squared. That whole thing also goes to 1, just like the way I reasoned about it before with the n cubed and the n cubed goes to 1. Limit is 1. Okay, so our limit is 1, therefore test is inconclusive. Inconclusive. So we need something else. We still want to make progress on this. So we go back and now we got to go back to our toolbox and we got to say, let's look through the different things in our toolbox. We ask questions like, is it geometric? Is it a geometric series? Where is n in a geometric series? Where do you see n? Exponent, right? No, so n is the base. These are just polynomials, right? So it's not geometric. Okay? So what about the divergence test? And that's a good place always to start. If your sequence doesn't go to 0, game over, right? If the sequence doesn't go to 0, game over. Does this sequence go to 0? The a-n sequence. N over n squared, yada, yada, yada. Yes, right? So n over n squared, when n gets large, it's basically n over n squared, which is basically 1 over n. That goes to 0, okay? So divergence test, inconclusive, right? Because we have a sequence that goes to 0. So what else do we have that matches kind of what we have here? Alternating. So this is an alternating series. And in order for us to conclude that it converges, we need to see that this part of it, right? So the part without the alternating part. So this right here, does it decrease to 0? That's what, if that decreases to 0, then the alternating series test says this converges. All that needs to do, what I circled in red, that needs to decrease to 0, does it? When n gets large, that's essentially, so as n gets large, that thing is essentially what? Like I said, n over n squared, or 1 over n. So does the bn sequence decrease to 0? It's essentially 1 over n for large n. You should be thinking yes, of course, that decreases to 0. And then in the alternating series test, that's all we need. So this is a convergent series. Now the question is it absolutely convergent or is it conditionally convergent? If it's like 1 over n, is 1 over n absolutely convergent? That's kind of what we're asking. Or the alternating 1 over n. We said no, right? We said no, 1 over n depends on the alternating effect to converge. Because without the alternating effect, it's like the harmonic series which diverges. So the ratio test is inconclusive. The alternating series test shows us that it's conditionally convergent. It's convergent, but it does need that alternating effect to do it. Questions on this example? So the ratio test is inconclusive. That's D, E, or F. But the series does what? Converges conditionally, F, by another test or test. Okay, question. That was a good problem. Lots of stuff going on there. Anybody have a question? Okay, next one. Let's just do as many as we have time for. Quiz at the end today. Quiz at the end today. Yeah, please. Oh yeah, just say something. Just speak out. Yeah.
Could you have used
What is the absolute convergence test? Is that from the book? I don't know what the absolute convergence test is. It wasn't a test. I was just defining what it means to be absolutely convergent. So, but yeah, that's essentially what we did. Yeah, so I just said, so what is, yeah, it's not really a test, but what is this series? Yeah, I think this is what you mean. This series is essentially, or is, that. So then we reason, is that convergent? Is that convergent? Yes or no? No, because what? So we could say, isn't this greater than n over n squared? If I make my denominator smaller, I get something bigger, right? And so what I have is essentially, I'm comparing it to, it's greater than n over n squared, which is the same as 1 over n. So the series that I have here is greater than the harmonic series. What's the conclusion about my series? Divergent, right? If you subtract from the denominator, you're going to get a bigger fraction. So the series that we're analyzing is bigger than n over n squared or 1 over n. So that's kind of a more formal way of saying what I said before. So now this is comparison, right? Divergent by comparison. But with the alternating effect, it's okay, right? Because as long as that thing goes to 0, decreases to 0. So when it alternates, it converges. When it doesn't alternate, it doesn't converge. And in essence, this is very similar to the harmonic series, because in the end, it's just n over n squared, which is 1 over n. Okay, yeah?
Do the ratio test and you find that it's inconclusive, will you automatically assume that either divergent or conditionally convergent will ever be absolutely convergent with different tests?
I don't know. Maybe. Did you guys know that? You understand this question? He said, if the ratio test is inconclusive, could it still be absolutely convergent? If the ratio test is inconclusive, could it still be absolutely convergent?
If it was not, then they would say that in ratio test. It wouldn't be inconclusive.
Okay, so the only chance is conditionally convergent.
Yeah.
So it's good question. Yeah.
So for the one that you have up there, if it was n over n squared plus 2n plus 5, it would still be conditionally convergent, but then our reasoning would work.
Yeah, you couldn't use the comparison test, but you could reason that what I said before was that in the end, for large n, it's essentially 1 over n. Even though you have a bigger denominator, for very large n, that goes away. Yeah. So this truly you can just use comparison. Yeah. Okay. Good questions. Any other question? All right, let's go on. Do more. Okay, so let's look at some of these. So are there any of these that we could, so we're going to use the ratio test on at least some of these. Are there any we could knock out without using the ratio test? So we come through here and we look at this first one. We're going to need the ratio test because it's not anything familiar, okay? How about this one? This we can do without the ratio test. Okay? We can definitely do this one without the ratio test. So let's talk about this one first. What do we have? We have an alternating series, and our Bn is essentially this. So let's start with just the alternating series test. If we do the alternating series test, does it converge? Does this decrease to 0? Yeah, really fast, okay? So like it's shooting down to 0 very, very, very quickly, okay? Because that's a huge denominator. When you get to 5, what is that? 120 times 32, already at n5. 1 over 32 times 120, already, okay? So this is plummeting to 0 very quickly. This is definitely at least conditionally convergent. So now the question is it absolutely convergent. So to do absolutely convergent, we're going to look at this series. Is that convergent? So what I see right away, look at this, 1 over 2 to the n. What's that? 1 over 2 to the n. 1/2 to the 1/2 to the n, right? What's that? You need to recognize that, folks. 1/2 to the n. What kind of series? Geometric, convergent or divergent? Convergent, r is less than 1. Yeah, people are not paying attention. You can't write in my review, he doesn't do enough examples, and then look at your smartphone the day I do all examples. Face buried in the screen. Okay. So this is a convergent geometric series, right? So can someone walk around? This is a convergent geometric series because it's 1/2. But what about the 1 over n factorial? Is that helping it converge or not? Yeah, so this is by comparison, we could say that this is, how does this compare to just that geometric series 1/2 to the n? How does it compare? We know that converges. How does ours compare? Less or greater? Much less. Much less. So we have what? We have a convergent series, or we have a series and it's less than one we know is convergent. That's the comparison test, therefore convergent. So that one is and absolutely convergent. Why? Because I took the alternating effect off. I took the alternating effect off, and it still converges. That's the principle of absolute convergence. So this one is going to be absolutely convergent. Okay, so looking at the rest here. This one we can do without the ratio test. Because I see this 3, I've got a bunch of 3's multiplied together here, and the denominator has a bunch of 3's multiplied together. So we can simplify that. We can simplify that. So how does that simplify? Do you see that? I have a bunch of 3's in the numerator multiplied together. I have a bunch of 3's in the denominator multiplied together. How does the number of 3's compare? Do I have more in the numerator or the denominator? More 3's in the numerator or the denominator? Denominator. How many more? 2 more. I got 2 more 3's multiplied in the denominator than in the numerator. So that whole thing is equal to what? 1/9. Not the limit. It's not the limit. It is 1/9, no matter what n is. Okay? That is 1/9. And suddenly this series became, it looked scary at first, but it became a lot easier. 1/9, 1 over n to the 1/7. Okay, so the 1/9 doesn't matter. If this thing diverges, then taking 1/9 of it is still going to diverge. If it converges, taking 1/9 of the terms, still going to converge. So the 1/9 is kind of a moot point now. What is 1 over n to the 1/7? What is that? That's a p-series. Is that convergent or divergent? So by itself, that's divergent, right? That's because p is not greater than 1. When p is greater than 1, the p-series converges. So now this p is less than 1, so that diverges. But what do we have? It's alternating. So with its alternating, all we need now is, does that thing decrease to 0? Does that thing decrease to 0? 1 over n to the 1/7. Does it decrease to 0? Yes. Yes. So because that 1 over n to the 1/7 decreases to 0, and we have an alternating series, that's convergent. But just the 1 over n to the 1/7, take away the alternating effect, it doesn't converge because it's a divergent p-series. So what's the final conclusion? Conditionally convergent. C. Okay, I'm looking at these other ones. So this one we could also do without the ratio test. So let's look at number 5. Yeah, but now it's times n factorial, right? So let's investigate. We got an alternating series. Let's investigate. Would be our Bn, right? That would be our Bn. Does it decrease to 0? So I'm gonna analyze this as an alternating series. Does it decrease to 0? So in order to look at that, how many factors does n factorial have? Remember, it's n times n minus 1 times n minus 2, all the way down to, how many factors is that? How many things multiplied together? N. What about the denominator? How many things multiplied together? How many 4s multiplied together? N. So what you can do in this sequence is you can match them up. So 1/4, 2/4, 3/4. Every factor in the numerator can get matched up with one in the denominator, and they match up perfectly. So then we get the first 3 terms are less than 1. 1/4, 2/4, 3/4. Then after that, what can you say about every one of these fractions? Greater than 1, right? These are all greater than 1. And as the sequence goes on, we keep multiplying by another factor, right? As n increases by 1, we get one more factor, and that factor is going to be a value greater than 1. So with each term of this sequence, we multiply the previous one by a number greater than 1.
So we're basically divergent.
Yes. So the sequence diverges. So by the divergence test, the series diverges. Okay? So that sequence is getting greater, right? It's getting greater as n gets bigger because we keep multiplying by a larger and larger number. So this sequence diverges. So therefore, the alternating sequence diverges. So if you have if Bn diverges, then the alternating version diverges. It just keeps jumping like this, right? Definitely divergent. I don't know what happened to B in the choices. Oh, because they match the letters match kind of what they are, right? Absolutely, conditionally, divergent. Okay, cool. So the remaining 3 would be good ones for the remaining 2 would be good ones for the ratio test, and there should be quick ones. Here we go. First one, ratio test. N plus 1 to the 6th over 7 to the n plus 1 times 7 to the n over n to the 6th is n plus 1 to the 6th. How about that part of it? N plus 1 to the 6th over n to the 6th. Limit 1. Should see that that's 1. Leading term n to the 6th. Leading term n to the 6th. How about 7 to the n over 7 to the n plus 1? How many more 7s do we have in the denominator? One more 7 in the denominator than the numerator. Yeah, Amber, question. Nice and loud. That one? Yeah, because if you expanded that, you're just, all you need for large n, you just need the leading term, right? If you expanded that, what would the leading term be? It'd be n, we'd have n to the 6th plus something, yada yada, n to the 5th, plus something, n to the 4th, all the way down to, 1 to the 6th. So when n gets big, what does the numerator essentially become when n gets really, really big? Just n to the 6th, right? Because that's always going to be n times greater than any other, at least n times greater than any of these others over here. So when n gets really, really big, these just disappear. They were just like 0. So you basically have n to the 6th over n to the 6th. Is it? Got it? Okay. All right, conclusion. Yeah, the limit's 1/7, right? The limit's 1/7, absolutely convergent. This one. Question? Other questions on that one? All right, so we got this one, number 4. It's going to be n plus 3 factorial. Yeah, thank you. And then 7 to the n plus 1, n plus 1 factorial. And then this will be 7 to the n factorial over n plus 2 factorial. Wait. This should not be here. I don't know why. Why did I put n plus? I was looking at a different problem.
You were looking at previous.
Okay, so is it just this? No, there is 2. I'm sorry, that's right. Yeah, that's right. Okay, we're good. Okay, so now we gotta resolve all these these factorials, right? All these factorials to figure out what we're gonna have from these factorials. So let's combine these two, because those were kind of together. N plus 3 factorial divided by n plus 2 factorial. If you can't look at that and do it, then you need to write them out. You need to write both of them out and figure out what it is. But basically, n plus 3 factorial is n plus 3 times n plus 2 times n plus 1. But I just started saying n plus 2 factorial, right? N plus 3 times n plus 2 factorial. Therefore, that equals, those two combined are just n plus 3. If you're not sure about that, you got to write them both out. Write them both out and see what terms cancel, or what factors cancel. All right, same thing with n factorial over n plus 1 factorial. N plus 1 factorial is basically n plus 1 times n factorial. So what happens? What does that become? N plus 1. So the blue ones combined give you n plus 3. The red ones combined give you n plus 1. Again, if that's unclear to you, then when you do these, you need to write out what those factorials mean and see how the cancellations occur. All right, what about the 7s? One more 7 in the denominator than the numerator. Conclusion, take the limit as n goes to infinity. 1/7 again, absolutely convergent. Okay, we're going to do one problem. You got a good one? Okay.
Also simplified. Alright. 3 for you to pick.
Oh, can you pick
This one, or
the one that's too hard, or just too confusing?
This one.
Okay.
That one's too simple.
Too simple? You think it's too simple?
Or, no, yeah, I was
This one,
saying
okay. All right, no talking, no talking. All right. Just put it at the top. Oh, this is really easy.
Yeah, that's what I was saying. So,
Something in between. Is there something in between? 4 to the n,
possibly that.
5 to the n plus 3. All right, let's go for it. See how they do.
This one. The other one they didn't teach you n times square root of n.
Yeah, that's just a lot of exponents, right? End of the 3 halves. I was going to do that one.
Negative sign.
Oh, yeah,
sorry.
so mean.